Hello everyone, and welcome to this new and exciting session in which we are going to see how to implement the GradCAM technique, which permits us visually explain how the deep neural networks work. This was first developed in this paper by Ramprasad et al. And entitled GradCAM, a visual explanations from deep networks via gradient-based localization. So as you could see here, we have this input. For example, let's reduce this. We have this original image, and then we could see this GradCAM output. Now the task here is a classification task where we're trying to say whether there's a cat or a dog in the image, and then with the GradCAM for the cat, we're able to detect the portion of the image which influenced the model to say that there's a cat in the image. And also for the GradCAM dog, we have this part here which shows us that this portion influences the model the most in detecting or seeing that there is a dog in the image. Now we also have the GradCAM for different models. You see this GradCAM for the VGG model, and we have this ResNet GradCAM right here. So we see that two different models can produce two different GradCAMs, though generally they should be similar. We see that with the ResNet, we have this larger surface as compared to this VGG, and we could also see this for the cat. Now that said, we are going to implement the GradCAM technique, which generates or which permits us to generate these kinds of visualizations which tell us what parts of the input influence the model in taking certain decisions. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. As we could see in this figure 2 from the paper, given an image and a class of interest, for example the tiger, cat, or any other type of differentiable output. So like here we have this image, you see the image, and we're given the class tiger, cat. So here the task is image classification. So here we have this class tiger, cat. Now for now we'll keep out this here. We'll focus only on this image classification. So essentially we have this image, as we've said already. We have the class, then we pass this through a CNN, that's a convolutional neural network. You have that right here where they say we forward propagate the image to the CNN part of the model. Remember, this CNN has already been trained, so we forward this to the CNN part of the model, and then through the task specific computations to obtain a raw score for the category. So task specific here, in our case our task is image classification, so this here is specific to our task, which is that of image classification. Now the gradients are set to 0 for all classes except the desired class. Then the signal is then back propagated to the rectified convolutional feature maps of interest. So you could see from here that when we forward propagate this to our CNN, we have this output feature maps. Here you have rectified conv feature maps. So these are feature maps, and then we pass this through this fully connected layers. Then we obtain the outputs. From here we back propagate, as we said already, to this rectified feature maps. And you can see that the resultant of this backpropagation is what we have here. Notice how this is colored compared to this. So here's our feature maps. Here's the output from backpropagation from this output back up to this feature maps. So we obtain this by doing the derivative of this output. Let's say y. Let's say y tiger cat. Let's call it tc. Y tiger cat with respect to x feature maps. Let's call it fm. So we finding or we computing this derivative of the output with respect to each and every value we have here for the feature maps, and obviously this will give us a corresponding feature map. It's just like having let's pick any position. Let's say this random position here. We take the output with respect to this, we take the output with respect to another position, take the output with respect to another position, and so on and so forth. And by doing this, we reconstruct somehow those feature maps, but this time around is going to be the derivatives of the output with respect to each and every position. Then from here, as you could see, let's take this off. From here, what we do is we are going to obtain the mean for each and every one of those features. So you see this one that's pinkish, you have this here. So we obtain the mean of for this. We take for this, we obtain its mean, this, and so on and so forth. So we obtain all this, and so all these mean values now are going to be multiplied by this feature maps. So for this, for example, this one here, we'll take this and multiply on this features. We'll take this, multiply these features, and so on and so forth. Then once we get this, we're gonna combine all this or add all these features up, and then pass this through a ReLU function, which then produces our GradCAM. And so that's how this works in theory. That's how we obtain this GradCAM we have here. Let's dive into the code and get this practically. So first things first, we have this EfficientNet B5 model which we had trained already. So we'll just load the weights. Let's go ahead and load this weights. So we have pre-trained model, load weights, and there we go. From here we could test out the model. So we have this image here. It's basically what we've seen already in testing. So we have the test image, we expand dimensions, and then we have the pre-trained model which now takes in our image array. So this is the output right here. You could see that the max is at this index 1, which is logical because it's a happy image. We could see that right here, the person is happy. So this is our image, and here's what our model produces. Remember, as we've seen already, we have actually 3 classes. We have angry, happy, and sad, and this is a 0th index, index 1 and index 2. So our output is index 1, meaning this prediction is correct. At this point, if you could recall from here, this model was broken up into 2 parts. So we have, let's take this off, we have this first part which generates this feature maps, and then this other parts which takes in the feature maps and then outputs the specific class of this input image. But given that when defining our model, this was in a block, that is, we basically define this as 1, not as 2 separate entities like this. We are going to look at how to separate this, or better still, how to create a model which is made of only this first part, and then a model made of this other part. And then one thing you should note is that the way we created this model was a bit different from what we had seen so far. So previously, if we get back here with those pre-trained models, let's get back modeling. We have pre-trained, well, let's pick this one, transfer learning with this. You see that we had a backbone defined, and then we have the backbone, we have global average pooling, and so on and so forth. And then when you look at the summary, if you look at the summary, you have all this represented as 1. So the backbone was or you don't get into the details of what is contained in the backbone. But now when you look at this other summary, let's get down to GradCAM. When you look at this model summary now, you would find that all the details of the backbone are given. And this is gotten differently because now what we do is the input, our x, which is passed into the global average pooling, is simply this backbone dot output. So when we specify that you want to get the backbone output, this permits us get a summary with all the details like this. And then when it comes to the inputs here, you would say you want to have the backbone inputs. So let's this input right here is actually useless. You could take this off. So that's it. So once you specify this and then you have your usual output, then you would get this full summary. Okay, so that said, now let's go ahead and create or make this model out of this full model we have here. So in order to create this last conf layer model, which is essentially this model here, where we'll get the output to be this rectified conf feature maps, we have this Keras model, which takes as input the pre-trained model inputs. So it's quite similar to what we had already here, where we'll just take the inputs to be the backbone inputs. Now our inputs is the full pre-trained model inputs, but then the output, take notice, the output is this last conf layer output. Now what is this last conf layer? The last conf layer is that layer whose name is given as top activation. You'll notice that this is this last conf layer where we have this feature maps. It's 8x8 by 2048, and then from here we move on to the global average pooling, dance 1, dance 2, and then we have our output. So this part from here upwards is this initial conf layer, or this convolutional neural network, and then this here is this classifier unit to the right. And so now that we have this name of this last conf layer, that's the top activation, we are going to make use of that to produce our output. You see, last conf layer is simply the pre-trained model, and we get the layer whose name is last conf layer name, and last conf layer name is top activation. So we understand where we get this top activation from. So now we have our last conf layer. As we've said already, we are now able to have this last conf layer model, or this initial CNN model here, which has as input the image and as output the feature maps. So let's run this and see what we get. There we go. We could do last conf layer model and check out the summary. There you go. We have this model. Let's check out the output. You see, here's the model output, and here's the model's input. See, 256 by 256 by 3. So we have the input is the image, and the output the feature maps. Now we've built this first model, or we've created this first model from our overall model. Let's go ahead and check out on our classifier model. So for the classifier model, you see we have this inputs. The input now is going to be this feature maps. Remember, the output of this was the feature maps, and the inputs of this is the feature maps. From here, given that we have the inputs to this classifier model, we are going to simply pass this through each and every layer which makes up the classification part of the pre-trained model. So if we get back up here, let's scroll back up, you'll notice that we had this global average pooling, we had this dance, we had dance 1, we had this dance 2, which all make up the classifier part. So let's get back here, and then you see this classifier layer names is given here, so we understand where these names are coming from. And then we simply go through for every layer name in our classifier layer names. So let's have this. So for every layer name in our classifier layer names, we are going to pass the input, this input, classifier input, into these layers. So we take this input, pass into the global average pooling, then the output will be X. We take that again, pass this into the dance, then we take that again, pass into dance 1, and then pass into dance 2, and then we have the output, which is in this case X. So our input is a classifier input, which is this, and our output is the output after we pass this input through these different layers. The conf block and the classification unit designed, the next step will be to compute the partial derivatives of the output with respect to the features here. Now we could compute this partial derivatives, or this gradients, making use of this gradient method, which takes in the top class channel and the last conf layer output. So this here is our top class, and then here we have our feature maps. To obtain this feature map, that's this last conf layer output, we simply pass the input, that's the image, into our last conf layer model. our last conf layer model is this conf layer or this conf model right here. Take the input, pass in here, obtain the feature maps. So here's our feature maps, and then from the feature maps we pass this through our classifier model. So we take the classifier, we take the feature maps, pass in the classifier model, obtain the predictions here, obtain those predictions, and then get the top prediction index. Now this top prediction index will depend on our example. Now given that the person is happy, we expect this index value to be equal to 1. So we could even print this out. Let's print this out, top prediction index. There we go. So we would have this top prediction index, and then to obtain the exact score we are going to simply pick that score from the predictions. So here we have the preds. Obviously the preds is from this, so we have the preds, and then by specifying top pred index or by simply specifying 1, what we're saying is we want to get the score when we pass this input into this classifier model. And now the score we're talking about here should be what we had right here. So it should be this value right here. So we're computing the partial derivative of the output with respect to the feature maps, and we're making use of this gradient method to help us do that. So let's take this off. You see here we have this here. There we go. We run this, and then we obtain this output shape. You see, takes the exact shape of the feature maps. Then once we have this here, that's this gradients, the next thing we could do is simply obtain the mean values at every position right here. So we'll simply make use of this reduce mean while specifying the axis. So let's run this and print out our pulled grads shape. There we go. You see we have 2048. So it's basically this vector now where each position is a mean of a single channel. Remember, from here we had 2048 channels, and each and every one of them was 8 by 8. So each, or we could say 1 by 8 by 8. So we had this for each and every channel, and now we've reduced each and every one of this into a single value. So this is just a single value, this is a single value, which we have here, which we could see here essentially. And so now we have this 2048 dimensional vector, and that's what we're seeing here. So this is essentially this. Now the next step will be to take this here and multiply by our feature maps. To carry out that multiplication, we'll simply go for I in range 2048. So for each and every one of these different positions we have here, we are gonna take the corresponding last conf layer output, which is essentially this feature maps. So we take the feature map. You see we specify I, so if 0, then we're taking this feature map of this channel and then multiplying by its corresponding pulled grads, which we've seen already to be the mean of each and every channel we have here for this gradients. So that's how we obtain this. Now note that we specify that we want this zeroth element because this is 1 by 8 by 8 by 2048, and specifying this will leave us with a tensor of shape 8 by 8 by 2048. So we get rid of this here. So that said, we now run this and we obtain our last conf layer output. So it's going to be obviously the same shape. You could see, check that out, last conf layer output shape, and there we go. Now to obtain the heat map, we are going to sum up the values at different positions for all the channels. So let's suppose that we have something like this. Let's say it's, for example, 3 channels. Then this position, see, we have this position, we'll take this plus this plus this, and then we'll have this output. Then we move to the next position, this plus this plus this, and then we have this, and so on and so forth. So that's how we're going to go from this 8 by 8 by number of channels output, or let's say 2048 output, to an 8 by 8 heat map. So this is what we have here. We're going to sum this and we'll specify that the axis is the channel axis. So we run this already, and then now we could visualize our heat map. But notice that there's also this ReLU right here, so we have the ReLU before we visualize the heat map. There we go. Here's our heat map, which we then resize using OpenCV's resize method. So you see how we get from this heat map, which was 8 by 8, to this one, which is 256 by 256. And the reason why we're doing this is because we want to add this with the image, or superpose this on the image, such that we have an output which shows us clearly where, or better still, regions of the image where we have the highest contribution to our output, which is that of a happy person. So the model predicts that this person is happy, and now we know which parts of the image contributed the most to that prediction. Now trying out with a different image and modifying this slightly so that we could get this image here, we find that is this part. So previously was the small region, now is this zone. We see this wrinkles right here. We have this zone and this zone which influence the prediction. And with this, we've just implemented this GradCAM method. Thank you for getting right up to this point, and see you in the next section.